So the assumptions that have been made, the very first assumption that has been made is that there are no forces of attraction between the molecules. So there are no forces of attraction or repulsion between the molecules of gas. Between the molecules. So this is the very first assumption, that the forces of attraction and repulsion, they do not exist between any two molecules. If there are two molecules, so there are no forces of attraction or repulsion. Then the second point that is given, taken as assumption, it states that this volume of the molecules, is negligible as compared with the volume of gas, as compared with the volume of gas or container. Since gases occupy all the space available to them, so we can say it to be the volume of the gas or the volume of the container, they are the same thing. Then third assumption that has been made here, we consider that the gas consists of a number of molecules. Okay? So here the next assumption is gas consists of large number of molecules. So the number of molecules which are there, it's very large number of molecules. Okay. Then we have concluded that molecules are in random motion. They are not stationary. Okay. So then next assumption that we have included, that the collisions between the particles. So the collisions between particles or between molecules, are perfectly elastic. So we'll see what are elastic collisions. Perfectly elastic. What do you mean by elastic collision? We'll see each of the point, why each point has been assumed. See, the first point says that there are no forces of attraction or repulsion between the molecules of the gas. So if you take in a container you take certain molecules. So we are assuming that since there is sufficient distance between the molecules, so because of that sufficient distance, there is no forces of attraction or repulsion between the individual molecules. So suppose I take a container here, and let's fill this container with a gas. So we have the gas molecules. So this container, it consists of the gas molecules. And the gas molecules which are there, they are in random motion. So as you can see, the number of molecules is very less. And since the distance between the molecules is large, therefore there will not be any forces of attraction or repulsion between the molecules. The second point, we assume that the volume of the molecules is negligible as compared with the volume of gas or container. So the gas molecules, they are very small. We know that the size of the molecules is very small. So that is why if you compare the size of that molecule with the size of this container, so it's very small. So hence we say that it's negligible. You can neglect the size of the molecules. Okay. Then gas consists of large number of molecules. How many number of molecules which are present in this container? It's relatively a very large number of molecules. For example, even if you take 1 mole of a gas, so 1 mole of a gas contains 10 to the power 23 molecules, which is very large. So even if you are containing 1 mole of gas, like 44 gram of carbon dioxide, so the amount of molecules will be 10 to the power 23. So the order of the molecules is very large. They are very large number of molecules. Then gas molecules are in random motion. All the molecules which are present in this gas, they are not stationary. They are continuously moving. Someone is moving like this, someone is moving here. So all the molecules, they are moving randomly. Some molecule may be moving here, some here. So in this way, the molecules, they are in continuous random motion. The molecules, they are not stationary here. Good evening, Jaswant.
Good evening, sir. Good evening.
Okay. So see here we are started with the kinetic theory of the gases, and we just observed here that the gas molecules, these are the certain assumptions which we take for study of the gases. Okay, so the very first assumption we have taken that there are no forces of attraction or repulsion between the molecules. Then the volume of the molecules is negligible as compared with the volume of the gas or container. Since if you keep a gas in a container, the gases tend to occupy the complete space available to them. If you put a liquid in different containers, the volume of the liquid remains the same, but the gases will occupy the complete space that is available to them. So hence, and also the distance between the molecules is too large. So you have here that the size of the molecules is negligible as compared with the size of the container. Then we have considered that gas consists of large number of molecules. The number of molecules which are present in a gas, they are very large. Yes, we say that if the quantity is very small, then we say it's negligible. Okay. For example, suppose if you are weighing gold, okay, and you are purchasing a 10 gram of gold. So with that 10 gram of gold, if you are getting some 5 milligram, so that is a very big quantity. With compared with 10 gram, 5 milligram is very big. But if you are suppose if you are getting somewhere 100 kilogram of grains, okay, so with that 100 kilogram, even a 10 gram or 15 gram would be nothing. So it depends if the quantity is very small as compared with the given quantity. So similarly here also the volume of the gas molecules is very small. Okay. Then molecules are in random motion. They are continuously moving. The molecules, they are continuously moving. They are not stationary. Okay. So here another important point we'll be discussing, that motion of the molecules. Okay. The motion of the molecule, that is, it determines the kinetic energy. We know that the formula of kinetic energy is given by 1 by 2 mv squared. So the kinetic energy of the molecules, kinetic energy will be equal to 1 by 2 mv squared. Okay. If we here we will not talk of the kinetic energy of each molecule, since we have considered that all the molecules are similar. There is no specific molecule with some specific criteria. All the molecules are similar. So here we will be discussing of the average kinetic energy. Okay. So we will discuss here average kinetic energy of the molecules. Since the molecules, they are in continuous random motion, the number of molecules is very large. It's not possible to determine the volume of the velocity of each molecule and find its kinetic energy. Okay. Since they are also suffering continuous collisions with each other. So due to the continuous collision, their velocities are changing. And hence, again, it's not difficult. It's not easy to find out the kinetic energy of each molecule. So we find out here average kinetic energy of the molecule. And it has been found that the average kinetic energy, it is dependent or it is directly proportional to the temperature. When I say the temperature, by temperature I mean the absolute temperature. So the average kinetic energy of a gas is directly proportional to the absolute temperature of the gas. Okay. So how it happens, in the last class we had seen that if you decrease the temperature, so what you are doing, you are taking away energy from the molecule. When you take away the energy from the molecules, so the motion of the molecules will cease, the motion of the molecules will slow down, bringing a temperature to a very low temperature, something like about, you can bring the temperature to be, if you are bringing it to be absolute zero, let's say you are bringing the temperature to 0 Kelvin. So at 0 Kelvin, all the molecular motion will stop. Okay. There will not be any energy available to the molecules for their motion. So we'll be saying here that average kinetic energy is directly proportional to temperature. Okay. And perfectly, if you write down the final expression, so it's average kinetic energy is given by the formula. Okay. Okay. So average kinetic energy is equal to 3 by 2 kT. 3 by 2 kb into T, where kb is a constant, and this kb is called as a Boltzmann constant. We'll study about this more in detail when we study about more details of the kinetic theory. But currently understand that Kb, it's a constant and it's called as Boltzmann constant. So we can see that kinetic energy is directly proportional to temperature. If the temperature is absolute zero, the molecules will not have any kinetic energy. Okay. If the temperature increases, the molecule will have small amounts of kinetic energy. They will continue their motion. Okay. So this is about the kinetic energy. Since all the molecules, they will be continuously moving. They are in random motion. So when they are in random motion, they will be in random motion if the gas has a certain temperature. If there is certain heat which has been absorbed by the gas, so the gas will have kinetic energy and which is a function of temperature. So if there is temperature, then there is kinetic energy. If the temperature is less, there is less kinetic energy with the molecule. Okay, I hope you have understood this point. Then molecules are in random motion. This we have discussed. Collisions between molecules are perfectly elastic. So what another word we have? Elastic and inelastic collisions. Okay. Collision, all of us know when two particles they come in contact with each other. So we call it as collision. So when two moving particles, or even if one of the particles is stationary, so let's say the molecules they are continuously moving. Okay, I'll explain about the Boltzmann constant. You can just remember its value, the value of the Boltzmann constant. See, to study the Boltzmann constant, we have some other variables. Like before you study the Boltzmann constant, you will need to study about the R, which is the universal gas constant. Okay, then we need to study some other parameters are also there. So that's why I stopped about the Boltzmann constant. You can just look for its value. You can keep the value of the Boltzmann constant. So you can check for the value of the Boltzmann constant. You can keep the value. Now, collisions between the molecules are perfectly elastic. Perfectly elastic means, see, if you observe the collisions in our surroundings, suppose we have a ball which we are throwing on the wall, or we have a ball which we drop from a certain height. The ball collides with the floor and then again bounces back upward. So during this collision, there is some loss of energy. That is why the ball is not able to come to the same height. Okay. It's losing its energy in the form of sound energy, heat energy. So it's losing its energy. So the collision of the ball with the floor. Just 1 minute. 1 minute, beta. Okay. So the absolute the collisions we were discussing. So the collisions in real life, they are not elastic. Over there, the energy is not conserved. During a collision, the energy is not conserved. There is some energy which is lost to the surroundings. But in a perfectly elastic collision, the total energy remains conserved. Suppose this molecule has a certain energy, this molecule has a certain energy, and these two molecules collide with each other. So when these two molecules collide with each other, there will be no loss of energy. So there is no loss of energy, and we call such energy as we call this collision to be perfectly elastic collision. Okay. So I hope you have understood what is an elastic collision, what is an inelastic collision. Inelastic collision means the collisions where there is loss of energy, and elastic collisions are the ones where there is no loss of energy. Okay. We'll discuss one more thing, that is momentum. Okay, yeah, energy will remain the same. For the total energy will remain the same. For example, this molecule has some energy Ke1, this molecule has some energy Ke2, and if they collide with each other, so total energy after the collision will remain the same. It will be Ke1 plus Ke2, it will remain the same. Okay. So these are the points which we have assumed. However, later on we will rectify ourselves. We will see that yes, all these points, they are not perfectly correct. Okay. However, we have assumed these in deriving the gas laws, in obtaining the studying about the gas laws, but we observe later on that yes, all these all these things, they are not perfectly correct. They cannot be perfectly assumed. For example, here we have assumed the first point, that there are no forces of attraction or repulsion between the molecules. But if you compress a gas, if you bring the molecules very close to each other, you will observe or there will be forces of attraction and repulsion between the molecules of the gas. Okay. So depending on our assumptions, we will obtain certain gas laws, and those gas laws we will be calling them for the ideal gases. We will discuss something as ideal gases and non-ideal gases. So let us see the gas laws. In the last class, we had studied about the three gas laws. The three gas laws we had studied here. We had studied about the Charles law, Boyle's law, and the Gay-Lussac's law. Charles law, Charles law, Boyle's law, and Gay-Lussac's law. So these three, they are the gas laws which have been studied by these three scientists, considering the three variables which I discussed here. In the three variables are pressure, volume, and temperature. These are also called as thermodynamic state variables, okay, or state variables of a gas. So to describe any gas, what we need to describe a gas, we need its pressure, we need its volume, and we need its temperature. So these are the three things we need to specify a gas. If we can specify the pressure, volume, and temperature of the gas, so we can describe the state of the gas. We can find out the what is the kinetic energy of the gas, and different properties of the gas can be determined. Okay. Now to study this, the efforts were made by these three scientists, Charles, Boyles, and Gay-Lussac. Okay. So according to the Charles law, we have studied in the Charles law that volume at constant pressure. Let's say the Charles law. What the Charles law stated. According to the Charles law, according to the Charles law, the at constant pressure. So first thing we have to keep the pressure as constant. I'll specify you how to make it. At constant pressure, at constant pressure, volume is directly proportional to temperature. Temperature. So at constant pressure, if you have okay, so if you take the pressure to be constant and you plot a graph between volume and temperature. So Charles, he plotted a graph between volume and temperature. So he obtained the graph to be a straight line, something like this. He obtained a graph like this, a straight line. So it showed that there is some, you can say that the volume is directly proportional to temperature. And at this temperature, let's say this temperature be T naught. So at the temperature T naught, the volume of the gas was V naught. So you can find out the volume of the gas. The volume of the gas at a given temperature will be equal to V naught plus some constant multiplied by the temperature. So this is how you will be getting the expression. So he went more further. If suppose he extends this line backward. So if he extends this line backward, however, practically it was not possible to obtain very low temperature. Okay, so whatever low temperature was possible, he did. But beyond that, it was not possible. Okay, so he extended the line backward, and while extended the line backward, he observed that this line of volume here at this point, we observe that volume has become zero. So at this point, volume is zero, and temperature that he obtained, the temperature was minus 273.15 degrees Celsius. So this was the temperature. That means he got that at minus 273.15 degrees Celsius, all the volume of all the gases will reduce to zero. Okay. So if the volume reduces to zero, nothing is left. You can see that nothing is left. If the volume has reduced to zero, so nothing is left out there. Volume has got zero. It's not even a fraction. So it means that practically it's not possible to have such a small temperature. But even if you somehow you are able to make decrease the temperature of any gas, so the temperature of that gas cannot go beyond 273.1, and hence he took it to be the 0 Kelvin. So now since the temperature were not possible to be below this temperature, and hence the Kelvin temperature is always supposed to be the positive scale. So I hope you got your one of the answers that why Kelvin scale is always positive. You might have heard in your class 9th and previous classes that Kelvin is the temperature scale which never goes negative. It's always positive. So now you have understood that why it can't be negative. Because at this point, at absolute zero, all the molecular motion will stop. How? Because we have seen about the kinetic energy also. See, the average kinetic energy we have seen 1 over 2 m v square, average kinetic energy. So this is equal to 3 by 2 kT. Okay. So if you get the absolute temperature as 0, so 0 multiply this would become 0, which implies that the kinetic energy of the molecules would be 0. That means at absolute temperature, all the molecular motion ceases out. All the molecular motion stops. There are no molecules which are moving. And as per the Charles law, we observe that at this temperature, the volume of the gas would reduce to 0. Okay. So therefore, if suppose molecular motion stops, so can you be living at that temperature? You can't be living. If the molecular motion has stopped, so that means your everything, all the molecules of your blood, everything is at frozen up. Nothing is there which can move. Okay. So such a temperature is called as the absolute temperature. So it was founded by Charles. Then later on, Kelvin devised it. The name obtained by Kelvin. So I hope you have understood what the Charles law says. According to the Charles law, the volume of a gas is directly proportional to temperature at a constant pressure. Okay. So you can remember this something like this also using some analogy like this. Suppose you have some gas over here. Now, since you have to keep the pressure constant, the pressure has to be kept constant. So you use a piston on the top. So on the top here, we have used a piston. So the piston can move up and down. This piston, it can move up and down. And inside this, you have your gas. So here you have your gas, and this piston can move up and down. Okay. So suppose it has a pressure P. It has a pressure P. Now, if suppose you increase the temperature of the, or what you can see, if you increase the temperature of the gas, if you supply some amount of heat, so that the temperature of the gas increases, and if the temperature increases, the volume of the gas will also increase. It will expand. Similarly, if you decrease the volume, the temperature will also decrease. So at this constant pressure. So understood about the Charles law. In the similar way, you have the Boyle's law and the Gay-Lussac's law. So let's see the Boyle's law, what the Boyle's law tells us. So in the Boyle's law, you have at constant temperature. You keep the temperature at constant and study the pressure and volume. So in the Boyle's law, it states that in the Boyle's law, we have at constant temperature. uh, At constant temperature. At constant temperature, the pressure of a gas is inversely proportional to volume. So, in the Boyle's law, we'll see. So here, the statement says at constant temperature, you have to keep the temperature constant, and you have to observe the variation of pressure and volume. So pressure is inversely proportional to volume, 1 by V. So if you increase the pressure, volume will decrease. If you decrease the pressure, volume will increase. So understand it from the previous one only here. Suppose if you apply some pressure on this gas, if you push it in the downward direction, so you are increasing the pressure. And if you increase the pressure, the volume of the gas will decrease. The space that is occupied by the gas will decrease. If you decrease the pressure, if you decrease the load from here, decrease the pressure, so the volume of the gas will increase. Okay. So this is pressure is inversely proportional to volume. And if you plot a graph between P and V, you will get a you will not get a linear graph. You will get a non-linear graph, something like this. So something like this you will get. So such a graph you will get if you plot a graph between pressure and volume. That pressure and volume, it shows that pressure and volume, they are inversely proportional to each other. What is from here we also get one point at constant temperature. If you have temperature at constant, so you can rearrange the terms and you can get here PV should be equal to a constant. So at constant temperature, PV is a constant. Okay. So this we got from the Boyle's law. In the similar way, you have the Gay-Lussac's law. In the Gay-Lussac's law, we have the variation of pressure and temperature at constant. So again, the pressure and temperature at constant volume, it gives that pressure is directly proportional to temperature. Consider here that the walls of this container, consider the walls of the container, they are insulated so that heat cannot escape out from it. And if you increase the pressure, if you push the gas, so you are doing some work on the gas and your work done will appear here as a form of increase of temperature or increase of kinetic energy. Okay, so our work done appears here on the gas in the form of increase of temperature. Okay, so this is our Gay-Lussac's law. It says that at constant temperature, you have pressure is at constant volume. Sorry, at constant volume, the pressure is directly proportional to temperature. So that is our Gay-Lussac's law. So I'm just writing the statement of the Gay-Lussac's law. In the Gay-Lussac's law, at constant volume, pressure is directly proportional to temperature. So now after combining all these gas laws, so once you combine all these gas laws, we get a gas equation, and that gas equation we call as PV equals nRT. So this equation is also called as ideal gas equation, or we also call it as the equation of state, as it combines all the three variables: pressure, volume, and temperature. Here P stands for pressure, V stands for volume, N stands for the number of moles, R stands for a universal gas constant, and T is the temperature. So all the gases which obey this law, they are called as ideal gases. So you'll see these are your ideal gases. We call it as ideal gas equation. Okay. And all the other gas laws can be obtained from here only. For example, suppose if you take the volume to be constant, so we get pressure directly proportional to temperature. If you get pressure to be constant, so volume is directly proportional to temperature. If you take temperature to be constant, so we get pressure is inversely proportional to volume. So all the gas laws, they can be obtained from the ideal gas equation. Remember, for obtaining the ideal gas equation, we have put certain assumptions. The assumptions of the ideal gas equation, they have been given here. These are the assumptions which we discussed in the beginning. So in the next class, we will discuss that how these assumptions have been used, how the gas molecule. Okay. So here we obtain that the average, with these assumptions, we have obtained the ideal gas equation. Okay. So anything, any doubt? Just one, any doubt?
No, sir.
Okay. So you see, we'll meet again in the next class. I hope you have understood about this kinetic theory.
Thank you, sir.